this is Vikram Katkar presenting you Eagle. Eagle is nothing but a PCB designing software. Today we are going to design a single side as well as a double side PCB like this. You can also design this type of complicated circuit using Eagle. See, in similar fashion, you can also go for this type of much complicated circuit. This is an Arduino board. So let's begin our tutorial.
Okay, here we go for tutorial on Eagle. Before directly jump on Eagle, let's have little basics on PCB. A PCB is nothing but a printed circuit board. Mechanical supports and electrical connect electronic component using conductive tracks, pads and other feature each from copper sheet laminated onto a non-conductive substrate. Here are some examples of PCB. As an electronic engineer, we know what is the importance of PCB designing. So there are lots of options available for PCB designing softwares in the market like Brutus, Express PCB, Sprint Layout, Dip Trace and Eagle. Among these, Eagle is most widely used and very user friendly. So today we are going to learn Eagle. What is Eagle? Eagle is nothing but easily applicable graphical layout editor designed by Catsoft, an award-winning software, and I already told very user friendly, which includes schematic capture, board layout and auto router, as well as give the facility like user language program, which will help us to simulate our circuit, to have a 3D visualization and many more. So we will follow these steps. Initially we will design our circuit, that is called schematic. Schematic is nothing but a circuit diagram of our project. You can see it in this image. Next, we will have a board layout, which is nothing but actual PCB and on which components are going to mount. We will decide the position, the routing, as well as how a PCB will look like. All things will be we will design this board layout. Next, at last we will have the 3D visualization of it. There are actually many types of PCB: single-sided, double-sided PCB and multi-layer PCB. But using free version of Eagle, we can go for maximum double-side PCB. So today we are going for single layer as well as double layer PCB. Before going to design PCB, it is also important to know packages of the component, how components actually look like, what are the sizes and what are standards of it. So there are mainly two types. One is through hole system and another is SMD. SMD is nothing but surface mounting devices, where the devices are mounted on PCB on the surface itself. But in through hole system, the components are passed through PCB, passed through holes, and they are soldered from the bottom. As you can see this in this image, where the resistor is passed through this hole and it is soldered from the bottom like this. Many examples are shown. In SMD components, the components sit soldered on the surface itself. You can see the sizes of it. There are many sizes. At last, whenever we want to produce our PCB in large scale, we actually send it to the manufacturer, PCB manufacturer, which use the CAM processor, which is nothing but computer aided manufacturing process, in which whatever file we will send to them, they will use it and manufacture it using machines. So here we go for the Eagle. Let's install the Eagle first. This is Eagle 6.5.0 version, which is latest. Initialize it. You can download this from Catsoft's official site, which is free of cost. Okay, now click next. This is the agreement file, ATS. Then this is directory file. Keep it as it is. Click next and then hit next. It will copy all setup files. Please don't cancel this one until and unless the setup get complete. Now it is asking for license file. If you have license key, then use this, but if you are a student, then you can use this run as freeware. That is a free version of Eagle. Of course, there are certain limitations, but it is sufficient for designing of engineering project as well as some small project. Hit next, then finish. It will delete temporary files and it will go off automatically. Now let's open it from the start menu. Search for Eagle. This Eagle 6.5.0. Open it. This will ask you to create a directory where our files will get saved. This is creating in C user documents and Eagle. Okay, in the documents, Eagle file is created in which our all the files like schematic and board file will get saved. Hit S. Okay. This is an error. Just click OK. Okay. Now this is the control panel of Eagle. You can see Eagle is nothing but easily applicable graphical layout editor. Fine. This is library file. Whatever components are there, the library files are here. In design rule, how the system will check our design. This is defined in the design rule. There are lots of ULP, user language program, which are very useful. This is just like a plugins in a browser. We used to plug in some plugin data in the browser. It is just same. In the Eagle, it is user language program. Script files are there. Then cam job, how we are going to produce the files which we can send it to the manufacturer. That is called, generally they are called as Gerber files. Here is the project. Now let's move on. Let's design one PCB and its schematic, board layout and 3D view. Fine. Now go for file, new project. It will make a one file in a directory whatever we just allowed to create, that is Eagle. Now it is let's give the name. Okay, today we are going to design a full wave rectifier, a bridge rectifier. So I'm giving name as a rectifier. Fine, just hit enter. This is you can say description space where the description of the circuit is given, used to give. For a time being, I'm showing you the one example. This is Arduino. You can see this example. Whenever I click this Arduino, it will give me little description of Arduino Omega 2560 reference board. Okay, the same way we wish to give the little description of our circuit. So just right click and edit description. Okay, now you can type in bold letter by using this B and type rectifier circuit. Fine. To use a para, just you have to give this one and give little description. Fine. Also you can say that this is a power supply. I think this is sufficient for our board. Hit OK. Now inside this file we are going to create our schematic, board, and whatever we want to do we will do in this folder. Fine. If it is closed, there will be no bubble. You can see if I double click, the bubble is gone. Now to open it, just right click and open the project. Sometimes this bubble is not there. You can see this. Initially you have to open it. Now in new, go for schematic. Schematic is nothing but a circuit diagram of our project. Okay, let's move on. Schematic. This is the editor area, or you can say canvas, where we are going to mount, rather we are going to place our component, and where we will connect them in a such a fashion to get a desired output. Fine. Initially we have two options to change the color of this canvas or editor. Go for option user interface. You can see it in the schematic. You have two option, black, white, as well as a colored option as well, but I am choosing a white one. You can also choose black one. Okay, this will give the white layout. This is actually origin. You can see this dotted plus. This is origin. Okay, before going to put all components on this sheet, we will initialize, or we will give one grid to this all the entire canvas. Just hit this grid button, or you can go to this view and then grid, then click it on OK on it. Style I used to use dot style. Then why we are using this grid? Because generally all components are in size of inches. They are in multiple of inches. These are the standards. Okay, maximally they are of 0.1 inches. Distance between two terminals are 0.1 inches, and sizes are in multiple of inches. So for better understanding, I am using mm on the board. 2.54 is nothing but the distance. It is in mm. It is nothing but a 0.1 inches. In multiple keep 1, and in alternatively keep 0.3175. Okay, sorry, 0.3175, which is sufficient to adjust the very small surface mount devices. Okay, let me show you few things. See, look at here. This is a datasheet of BC 547546. Okay, in that, distance between the two terminals is of 1.27 mm, which is just half of 2.54. Similarly, in another datasheet, you can see the distance between these two terminals is 2.54. Okay, this is datasheet of LM555 timer IC. Again, you can see this in Atmega 328P. The distance between two terminals is 2.54. Fine. That's why we are using this grid, whose size is defined as 2.54 mm, 1 in multiple of 1, or in alternative key 0.3175. You can also use 1.27 in multiple of 2, but I am using 2.54. Okay, just hit OK. Now you can see these dots. Fine, which is not visible very clearly, so I am using lines. Okay, fine, you can see it now. Distance between, or you can say the size of the square, is 2.54. Any component whatever we are going to add here, this will automatically adjust in these 2 points, or in multiple of these 2 points. Okay, this is the center. This is dotted plus is nothing but a center. Okay, now we are going to add our components. You can see this add button. This is the add tool. You can click for adding the components. Fine, this is nothing but all library files. in which all things are get included, but some components are not there, like gas sensor and all others. This is the already defined, already given by Eagle. If you want to add something extra, you can also download it from any site. Just hit search it on Google. You will get a library file and then add over here. How can you will add? Uh, Let me close this. Just go to program files where you save your Eagle. You can see this in the library. Now copy paste over here the file, whatever file you downloaded. Look at here, this is the solder library file or LN35 library file. I'm copying it, and in C program files Eagle in library files I'm just pasting it. Okay, this is the LN35 temperature sensor IC. I'm included this library over here. Okay, now just close this, and in this canvas we have to tell the Eagle, we have to tell it that use that library file. So library use. Now just we added the one library, that is LM35. You can see it, this is LM35. Okay, now just control all for the selection of all files, because we will need this all file. Now just open it. Fine, it will take some time to load. Now go to add button. Now you can choose your any components whatever you want. Okay, it will take a little bit time to understand how the library is set. Like many things are you will not find directly, you have to search it for it. It will take some time to learn. Okay, now we are going to design a rectifier, of course. So we will need a diode. As I said, full wave and a bridge connection. We are using bridge connection, so we will use 4 diodes. Now you know 1004, sorry 1 and 4004, 1 and 4007. These are general purpose diode. You can see it also. It is a general purpose rectifier diode whose maximum current is 1 ampere. Okay, diameter is 2.54 mm. Horizontal is nothing but a position. In this image or in this window you can see the symbol of it, and in the another image you can see the top view of the component after placing it on a PCB. Here also it is written horizontal. This means this component is horizontal, and this grid is very important. This will give the total idea about total distance between the component and total idea about the size of the component. It is a 10.16 mm. Okay, I'm using it. When I just press OK, the component will be in my hand. It's on you where you want to put it. Okay, now I will suggest just play around this center, which this will help to in the Gerber file. The component places are defined from this center, so it is very important that you should always play around the center. Now the component is in your hand. To rotate it, just right click once, continue. If you want to rotate in another direction, I am keeping it vertical. Now I wish to put it over here, just one click. Okay, it will place the diode. Now still this component is in your hand. Now if you wish to copy, or if you want a multiple of that component, then just put it continuously. I'm using the 4 diode, so I put it for the 4 time. Now just press escape to go to library again. It will take you to at the same position where you left. Okay, now decompress it. Now I'm using one regulator IC 7805. As I mentioned in that description, 5-volt power supply. So I'm using a 7805 IC, which is in the library of VREG. Here you can see voltage regulator library. In this 7878 XSL, you can choose anyone. This is a small set transistor, and this heatsink is quite large. There are lots of type. So to design a PCB, you should have a little bit knowledge of how component look like and how the component we usually mount on the board. So I'm using this 78 cross L, that is 780. I can name it 7805 LIC. Just hit OK. Never use this drop button. If you use this drop, this library will go off from this software. Okay, so just ignore this drop button. Now I'm choosing 7805IC. Just hit OK. Now it is in your hand. Just right click to rotate it, and you can scroll down to zoom out or zoom in. You can use mouse. It is recommended to use extra mouse. Fine. Now I'm putting it over here. Okay, you can see this IC is by mistake I put it. Don't worry, I can delete it later on. Now again press escape. Now decompress it. Now I know I will need one transformer, 2 capacitor more, and 2 more connections for the output. Okay, we know that transformer is generally not put it on PCB, so we will give 2 solder pad over here and 2 solder pad for output as well, where we can connect the transformer and output through wires. So this can be found in solder pad library. Expand it and choose any one. I'm choosing this LSP10, which is of 1 mm diameter drill. Fine. Now hit OK. I needed 4 of them, 2 for input and 2 for output. Okay, now again hit escape. Now to get a capacitor, I can go for C, that is I can search for capacitor as well, but you will get all these things in RCL library, in which resistor, capacitor, inductor are included. Okay, you can see it. C polarize, E, L, as well as R, and potentiometer as well. So for the capacitor, generally use a US standard. I prefer to use US standards. You can also use any one. We know that our capacitor is polarized. For the ceramic capacitor, you can choose this CUS, in which you will get a ceramic capacitor. This is a top view, but I need a polarized capacitor. So search for the capacitor which is known to you. We generally use a round shape capacitor in power supply. Okay, like this. I got it. Okay, you can choose any one. Use in reference to this diameter or grid size. Okay, I'm using 5 mm size. Hit OK. You can use any one. To rotate, if system is in your hand or any component is in your hand, you can rotate it using the right click. Fine. Put it somewhere properly. As per the datasheet mentioned, they mentioned that use 2 capacitor, one is in input and one is in output for proper stability as well as filter purpose. Fine. I think we need a ground terminal, right, which will use to ground the IC as well as all other component. So search for supply 1, in which you will get all thing, plus 5 volt, VCC, ground. I am putting ground first. Okay, ground over here, as well as I am putting this plus VCC over here. Now again escape. Okay, I think we have all thing to design our circuit. Now to come out of this panel, just click cancel or again press escape. Fine. Now for the proper visualization, now you can see this IC is not visualizing properly, so you can zoom in or you can zoom out for proper visualization. Otherwise we have a short key Alt F2. Okay, system will automatically take this all component and properly show you on this canvas. Okay, now I just want to delete this first. Use the delete tool. Fine. And generally each and every component is characterized by this plus sign. Okay, this plus sign means that is the center of that component. So for deleting, just click on this center. Fine. Okay, let's move on. Now to move any component, we have a move tool. This is a move. Just click once. Now left click on any component. That component will come into your hand. Now it's on you where you want to put it. If you want to rotate it, just rotate it, because I said already, if component is in your hand, then just single right click can change it by 90 degree. Fine. I think this position is well and good. Well, very well. Okay. Now I am little adjusting my all components properly. This ground over here, this over here, and this over here. Okay. Fine. And here you can see this name is creating little bit problem and congestion as well. So as I said, we can access this IC using this center as well. If we want to access this name, or you can say the value, we need one center for them as well. So use the smash tool and click at the center of any component. You will get a 1 plus over all the names and the value. See it over here as well for this one. For this, I used to do it for all one, because at any time I may need to change the orientation or this name as well. So now you can access those name and value. Just say click on the center, that name will be in your hand. Okay, now you can put it over anywhere you want, but I recommend you to put it near the component itself. But for time being, I know what type of diode I am going to use, so I just want to delete this name. Just use a delete tool and click it at the center. Okay, or you can say the access point. Fine. Now let's adjust the name. For the rotate, I just click right. Now you can see this name also moves in the two boxes. Remember, I said the grid at such value, all the components get fitted on in this grid itself. You can see it. Okay, and I will recommend you to put the all component in the grid itself, because it will help us in the connection as well. Fine. If I click on any name, this name also will move in that grid. So if I want to put it properly, do you remember we gave alternative key in the grid, alternation factor 0.3175. Now just press down the alter key from your keyboard. You can see the name can move anywhere very fluently and smoothly. Fine. That's why we give the alter key as well. In alter key, 0.3175 is the size of small SMD components, so we use that 0.3175. In the same manner, I will just adjust this name LSP1 as well. Now D1 also. You just need to press down the alter key to adjust it properly. Fine. We don't have the plus sign or access point of this C1. Actually, we missed it. Again, use smash button and just click at the center. Fine. Alter F2 for proper visualization. Fine. Now we will connect all these component. Using proper wire. For that, choose this net. This is a single wire. You can say single line bus, or you can use this bus option as well if you want to connect multiple pins. Just like in microprocessor, microcontroller, the address pin and data pins need to connect with the multiple data pins of any other devices or peripheral. In that case, we can use this bus option. But for time being, we are using this net. Initially, we will connect all these diode first. You can see, just click at this end, just left click, the wire will be connected first over there, and another terminal is in your hand. Now you can move it anywhere where you want. I wish to connect over here, just once click, it will connect it. If system is not get connected, see over here, I'm just clicking once, the wire is placed over there, but as a circuit is not completed, or you can say the connection is not completed. Here there is no component, that's why the wire is still in your hand. Okay, so be aware that you can just escape to leave that wire, but this connection is wrong, so we are going to delete it using delete tool. Now again I wish to connect this diode over here. Now here also I will connect. In the same manner I will connect this input as well, which will come from the transformer. Now see over here, as I connected this pad to here, it forms one junction, that is here two wires get connected. That's why automatically this is a net, is placed by the software, because we are using this net. That's why it put automatically software put the dot over there. See once more. Okay, this dot or this junction ensure that the connection is proper. Fine. Now again I will connect all this one. See, now the system is going little bit, it's not looking nice. So I will go up first, then click once and then go right. Okay, you can do this. Fine. Now connecting ground again. Fine, got it. Now this C++ over here. Okay, this is showing the merge net segment NS$5 to supply net VCC. NS$5 is the name given to this segment. Okay, now as we connected VCC to this segment, it is showing, it is giving warning, or you can say it is just a declaration, or it is a declaration. Just hit yes. After that this will connect the wire. Now we need to connect over here again. Yes, same thing may happen with the ground also. Fine. Now this over here, this over here as well, this is a ground terminal. That's why you can go from here also, but it will not look nice. That's why like this. Again merge the segment NS$4 into the supply net ground. Just hit yes. Okay, now Alt F2 for a proper visualization. Now a circuit got completed, but you can see that it is not looking proper, or it is little complicated. We can make it simpler. Fine. So for that I'm using delete tool to delete this wire, some wires. Now look how I just make it compact. Fine. So I need this ground terminal to be here and ground terminal to be here as well. So I'm just copying it through this tool, copy tool. Fine. Just click once, the copy of that component will be in your hand. Just put it over here. As I put on that wire itself, that's why it automatically get connected. So it is going a warning. Just hit yes. Now again I need one more. Just click once, the copy of that component will be in your hand. Now put it over here. Fine. Now connect the wire. Fine. Now again little more spacing is there, so I wish to adjust all this group to closer to this circuit. So I can use this group key, group tool. First you can see over here, left click and drag to define a group. Just drag it to define a group. Okay, you can see the color of that the group is changed. Now use this move button, but left click to select an object and control plus right key to move the group. It is saying that press down the control key and just hit one right key, all the group will be in your hand. Fine. Now you can release a control key also. Now just adjust it wherever you want. Okay, to put it down back on the layer, just hit any key once. Key of any mouse. I'm using left click, just click once. Fine. Now it is looking a little bit proper. Okay, our circuit got completed. Fine. Now to check the connections are proper or not, or you can say this IC get connected with capacitor or not, the grounding is right or not. For that we have this I tool. Okay, show tool. Using this, if you click on any junction, that will highlight all the components and all the wire which is connected to that junction. Fine. This is connected to this one, and also you can see this is in red color now. For this junction as well, all the three components are connected properly. For this as well, this wire is also properly. Okay, fine. Now as well, we have another option or another tool to check this all the connection, that is called as ERC, electric rule check. Now click on it. It will give all the information about whatever error are there. Okay, just like this one, this is a warning, not an error. Part C1 has no value, part C2 has no value, and part IC has no value. It is showing that we didn't give any value to this C1, C2 and this IC. Okay, it's on our hand which type of which value of capacitor we are going to use, but you can also give the name in this eagle itself. Now click on this value button. Fine. Now click on any component and give the value. Like I can say 100 microfarad here. Enter OK. For this capacitor also 100 mu F. Hit OK. For this IC it is 7805. And hit OK. Now again I wish to move that all in proper way. You can use alter factor, and value are given properly. Assume that while connecting the wire, this dot is not placed by the software, or you can say we missed it, or the connection is not proper. Okay, by mistake it is happened. In a complicated circuit, we can't visualize a small dot or small junction, but okay, this is a simple circuit, so we can visualize it. But in complex circuit it is not possible, so this ERC will help much more. Just click the ERC. It will say that close button connected wire is in net NS$6 and NS$3. It is showing that these three wires, or you can say these two wires, are not connected properly. Okay, and saying only one pin on net N$3. This means that on this segment only one pin is there. Okay, this means that this connection is not proper. So for that we are going to place one junction over here. You can choose it from here. Now just put it over here. It is saying that merging these two segments, just hit OK. Fine. Now again rule check. It is showing ERC no error warnings. This means the circuit is error free now. Just press Alt F2 for proper visualization. Fine. Okay, I think this is sufficient. I think I covered all topics from over here. Now for the engineering project, we wish to export this image as well. So initially I'm going to put a one frame over here. Now you can search for frame, which will this frame will help us to just make up on a circuit. Fine. Put any one frame. I'm using this frame. Okay, I think we missed this origin, so I will move all this group first to the upper side and this frame over here at the origin exactly. Fine. Now press the Alt F2. It is looking nice now. I can also put my text, my name or circuit name over here. Just put it. I am putting rectifier and my name. Okay, hit OK. You can see it in yellow color, but actually it is very less size, so increase it from here. Size option, I'm choosing 3.81. now you can see it. Okay, rectifier. Using this ratio you can bold it properly, much more bold option. You can see it if I am choosing 31, it is more bold. Okay, we have three fonts: vector, fixed. I used to choose vector because it looks very good and fashionable as well. Now to check this ratio, much more bolder if I am choosing higher ratio. Okay, 10% is comfortable. Fine. Now put it somewhere wherever you want. Generally I put it over here. Fine, just one click. Still this name will be in your hand. If you want to put somewhere else also, you can put it wherever you want. Put it and then press escape. Again you want to write something about something about the circuit, you can write over here and just hit OK. You will get that text. Now just press escape again to come out from it. Fine. Now just save this file first. Okay, as I said already, this is my computer, my documents, eagle, this is directory, and rectifier is my file whatever I generated before, and just give the name to this schematic. I'm using rectifier itself. Okay, rectifier schematic. Save it. Fine. Now you can find it from here in the documents. In eagle file there is one file rectifier, in that schematic. Fine. Rectifier SCH file is nothing but a schematic file. Whatever this we are dealing with is a schematic file. Now as soon as I saved the file, the rectifier, date, time and the number of sheet automatically came over there. Fine. This is all about schematic. Fine. Let's move on to board now. You can use this hotkey to switch to board or generate a board file. Okay, just click once. It will give the warning that a board file is not created before. If you want to create it now, just press yes. Okay, it will create a board file for us. Fine. Again I said you had to put grid again and again. Whenever you're opening any file, you have to put the grid. Okay, I'm using lines as well, mm and mm. 2.54.3175. hit OK. Fine. Now from the option you can choose the user interface, whatever layout, black, white. For the time being I am showing you the black one. Fine. Now this rectangle is our PCB, size of our PCB, or you can say border of our PCB. You have to adjust all this component over here. You can also enlarge it using move tool. Fine. But actually Eagle free version of Eagle allows you to adjust all this allow this size of PCB only. You can't exceed it. Now using this move tool, just pick up any component and place it over here wherever you want. Okay, I said you already, just click at the center. Okay, if you click at somewhere else, this component will be not in your hand. Okay, just click the center, the component will be in your hand. Fine. In the same manner I am bringing all the component. Fine. Put it properly and try to minimize all the cross connections. Fine. Now you can see this one is for output, third and fourth one, and this one is for input. I'm putting one by one. Fine. Now you can reduce the size of your PCB because this one, all these components are already included in this size, in this area. So reduce it by clicking at the center of line. You can pull it down, just drag it. Now again you can just click the center and you have this all the frame in your hand. Okay, I reduce the size of PCB. Now we have one tool called as rat nest. You can see at the dialog box, this is the dialog box, see over there, calculate the shortest air wire. This rat nest button will automatically calculate the shortest distance between any two terminals. Now look at the circuit, I am hitting the rat nest button. You can see this, the wires get simplified. Fine. Okay, now we will use the auto router, which is a very great function for Eagle. Just hit this auto router button. Fine. Now Eagle allows us to use a double side of PCB. In free version we can use a double side PCB only, but actually there is a 16 layer PCB can be designed using this Eagle. Fine. For the time being I am using the single side PCB, so I am telling this top layer to not applicable. To the bottom layer, this vertical line means only vertical connections. This little tilted line means only tilted connection. In the same way this one, and this star means all connections are possible, or we are allowing Eagle to do all type of connections. Okay, top layer is not applicable and bottom layer is used. Now just hit. There are lot of options. They are optimize 1, optimize 2, 3 and 4. They are generally used for multi-layer PCB. For the time being, just ignore that one. Just hit OK. Now you can see Eagle search for the most great option, you can say, as well. It will try to connect all the air wires properly, and you can see this 100% finished. Fine. It will optimum the routing and it will give the final product to us. Alt F2, you can use Alt F2 any point of time. Okay. Now our circuit get completed. You can see the all components are connected properly according to our schematic. You can switch to schematic. This is our schematic. Fine. Now you can see it in both. These two inputs will come from transformer, and this is for the output. Okay. Now if you wanna connect it by your own, you can also use this route tool to connect it. For the time being, I'm unrouting any one wire. Check it out. Okay. Now you can connect it using this route tool. You can see this. It is moving in rectangle only because it is a rectangle is chosen. Wire bend is chosen. Now choose this wire bend another style. This will move the all wires in little angle. Right? Now you can hear the sound. This wire got connected. Again this wire is remaining. Now I can also connect it through. You can see this how I am connecting. Fine. This wire, this connection goes from the bottom layer. This component will be at the top layer, so there will be no interference. This is not connected to this diode, and this follow this path and connected to this supply. Fine. Now I used to connect all the wires by my own, and very rarely use auto router because it is good habit to connect the wires by your own. Fine. Now check it out how I am connecting the all wires. Generally we never use this bend, right angle bend. This will create unnecessary noise problem as well as it will increase the resistance resistance of this wire. So unroute it and do the proper connections. Fine. You should frequently hit the ratness button because it will bring out the hidden one also. If you connect some wire and another wire got hidden, then it will be very difficult to visualize. So frequently use this redness button. Now you can see this. I'm connecting another wire, but this wire got in cross connection. Fine. So if I connect this to this one, yes, it will be in cross connection over here. So this is not allowed because we are using single side, so wire shouldn't get crossed. Fine. So see how I am managing it. Is it fine now? I'm taking it from the bottom of this diode. Fine. Now my circuit got completed. Filter F2 for the proper visualization. Now I can check the same thing I did in the schematic. I use ERC. Here we have one option, DRC. DRC is nothing but a design rule check. Just hit. This will give the all information or all errors regarding if two wires got overlapped, or if some wire is going very close from any pins of any other component. You can see the different options. The default values are quite good. Just apply and check. It said that there is no error. Assuming I took this wire from here very close to from this connection, then it will show me the error. Now we can see one wire is still left. I should connect it. Fine. Now all connections are done properly. Now we can see these values and names are overlapping. Same thing was happening with the schematic, and we use the smash tool. Similarly, we are using smash tool over here also. Fine. Now I am managing these names. 100 microfarad. Use Alt key for smooth variation or displacement of that name. Fine. Now I wish to delete this name, or you can keep this name also, because this will, if we are sending this to manufacturer, whatever these names will be printed on upper side by some ink. Fine. Now okay, final step, never remove all the copper from this area. In the simple words, we can say I will fill this remaining area with the copper. It will help me for the heat sinking purpose. Also, it will help me to reduce noise and many more. Also, it will save my copper. So I'm using this polygon symbol, polygon tool. Using this, I will cover this all the empty area with the copper. See, use this style, use this wire style. Now I give the isolation factor. Isolation factor means it will keep distance from the all other wires. You will see it very soon. Choose with point it. Now draw it properly at the border of your PCB. Fine. It is whenever it got close, line will be dotted. Now use this redness button. Now you can see this. Fine. This goes out, so you can use Ctrl Z option here also. I'm doing it once more. Isolate factor pointed, width pointed, and this wiring style. Fine. Okay, now hit right next. You can see it. Isolate factor is nothing but, in the isolate factor, the distance from system automatically remove little bit copper from the mm, wires near about 0.8 mm distance is kept, and all other copper is removed. You can see it. Now I wish, if I grounded this copper, that will help me for a heat sinking purpose. That's why I am renaming it that a polygon. Just choose this renaming tool, hit at any corner or any border, so that you can see this polygon is highlighted. Now give the name ground GND and hit OK. Now you can see all the system is grounded, so this wire got hidden. That means this ground pin is connected to that polygon, or you can see copper sheet. This another terminal is also connected to ground. One terminal of this capacitor, one terminal of this capacitor also connected to ground. One terminal of this diode is also connected to ground, and another is also ground. Fine. It will simplify our circuit as well as save our copper, and it will help us to reduce noise and give proper heat sinking. Okay. For that I generally keep the copper. Fine. Now we can move on. This is my final design. You can see this layer button, layer setting. Using this layer button, you can see the bottom layer, top layer, pads, vias, dimensions, this component, that is T place, T names. Using this, now for the time being I am just removing top layer and apply. Fine. As we know, we didn't use a top layer, therefore no top layer is removed. Now for the time being, T place, B place, T origin, T name, sorry, not a B place, T origin and T names are also removed. T values are also I unchecked it. Now apply. You can see it. Only bottom layer. These are the pads. Okay. We didn't use vias, that's why no vias are here. Vias is nothing but a connection of top layer to bottom layer, or in multi-layer connecting at two layers. We use vias, in which hole is made and the hole is totally filled with the copper, or you can say any material which is connecting, which will connect our top layer to bottom layer. Fine. You can see using this layer button. And for the time being, we just need a bottom layer and pads to print on it, on the sheet, or you can say to print it on copper plate PCB. So that I'm choosing bottom layer, pad. You can choose vias or not, because we didn't use vias, and dimensions. Just hit apply. Okay. Now you can see this. This is the copper sheet. This is vias, and these are routing wires, or you can say connecting wires. Fine. Okay. Now you can also send a Gerber files to manufacturer to manufacture PCB. But if you send a file and you tell them to manufacture just single PCB, they will cost very high to you. So that we use a general method, or you can say very popular and cheap method. What we do, we use to print this on a photo paper, whatever it is, and then we generally then impress it on a copper plated PCB, where all sheet is of copper, and then we put it on it using iron or something heated element. We press it from top, and this color of that paper will impress on that copper, and then we will wash it, the remaining copper, from the using FeCl3 solution. And for that you just need to print this circuit. Now you can see it in this image. choose a A4 sheet, and I used to save it as a PDF first because I don't have a printer at my home. That's why I save it to PDF. Then I will take it to any printer and I will print it. Now just uncheck this mirror image, okay, because we need it. Whatever sheet, whatever image you are seeing in this layer board layout, we just want that one, because whenever we are going to impress it on copper PCB, it will come at a right place in right proper orientation. Fine. For the printer, choose PDF. Output file, it is same in that Eagle library, Eagle directory, rectifier and rectifier.pdf. Now you can choose the alignment, choose it center, wherever you want. Area, choose always full one, and use black and solid option. Okay, if you didn't choose it's on you if you want a black or solid, black or not. I used to choose black and solid option. Just hit OK. Now go to that library again. You can see this rectifier's PDF saved. Fine. This is your PCB layout. Okay. Now print it and impress it on a proper copper plated PCB, and then wash out using FaCl3 solution. Fine. This is all about Eagle. Now you can display all things. Top, Vias, dimension, T place, bottom place, T origin, B origin, T name, B name, T values, B values, and apply. Is it? All the component is shown. Now just save it. Fine. This is all about Eagle. Now this is all about board layout actually. Now let's have a 3D visualization of our circuit. For that we have to install one software, Eagle 3D software, which is free of cost. You can search it on Google. I'm just installing it. Choose language, Eagle 3D setup, next. Keep the directory as it is, next, and install it. This will generate a file which can be viewed using POV Ray file, POV Ray software, which is also free of cost. You can search it on Google. Persistent of Vision Ray, this is software full name. Click next. I accept. Next. Next. Install it. It will install that POV Ray software. It will take a little bit time. Let it get complete. You can see it is complete. Just hit finish. Now open this readme file. Fine. There are some initial settings we have to do. That is, we have to give a library file to this library file, or you can say library directory, or you can say path to this file, to this software. Okay, which can be done. It should be done using this tool edit master pov.ini. Okay, this is a text file. Now just copy this library path over here. Fine, at the bottom. Yes, you can read this. Necessary. So in those case, you don't necessarily have to have anything at all here. This path is library path. C program files equal ULP equal 3D POV array. But let's check where this actually file is. Eagle ULP equal 3D. Now I am going to my computer, C drive, program file cross86, and you can see this is saved over here, Eagle ULP Eagle 3D, and then POV. Okay, all the POV array files, whatever the data it is here. So now you can see this. It is little bit different. Program file cross86 is over here, but here we place program files. So just copy it, just click once and copy this directory and paste it over here properly. This C to this POV array, just paste it. Fine. Now you can see program file cross86 equal ULP. Now just file and save it. This is the one-time setting you should do before using that POV array software. For time being, I'm closing it. Yes, reload it. Close it now. Fine. Now go to rectifier. Fine. Let me tell you a little more about ULP, user language program. User language programs are the program, you can say, external plugins used in Eagle software, using which many operations can be done. For the time being, I'm showing you one example. Just type run in a command box. This is called command box. Just hit enter. Fine. It will open the inbuilt ULP for you. Here we have a lot of options. Okay. Many of them are very useful, but for timing I'm showing you one. Just find a rename schematic. Or a renumber sheet.ulp. This file will renumber from the top to bottom if we are using multiple components like capacitor, register in multiples. You can see C1, C2 is over there. Fine. You can just choose the serial number and hit OK. It will automatically renumber all the components from top to bottom in ascending order or descending order, whatever you choose over here. That means whatever comes first, that will be named as the first one. In this C will be named as C1, this will be named as C2. If another C is over here, it will be named as C3. Fine. In this way, this will be very useful. Just hit OK. Fine. It automatically renamed it. Grid is gone, so you can also hit OK. Fine. As we didn't use multiple, this is so that you can't see over here. In the same way, the 3D visualization is done using ULP itself. So in the similar way, we are going to type run, then hit enter. Now we are in board layout. Okay. In board layout, we are typing run in the command box. Hit enter. Now again it will open ULP folder, but in this whatever 3D ULP we need, it is not here. So let's browse it where we save it. Just go back to program files, it is cross86. Now choose this Eagle, simple Eagle. In this Eagle we have this Eagle 3D ULP. Open it and choose 3D 41. In this 41 only, all the component file, you can say, it will generate a POV array file, persistent of vision file, which can be seen using that POV software. So select this 41 always, open it. Okay, just this will ask for single time. Choosing English. Okay. Okay. Now it will ask for the output directory file. You can see over here. I am giving output directory file this Eagle itself. documents and eagle. Okay, just select this one. This is the main control panel of that POV array file. Now you can see eagle 3D input parameters. In the destination file, just set to board file. Wherever we are going to save all files in this rectifier file. Okay, so all the files will be saved in rectifier files. Now go to board and just hit 100 over here. This is the rotation angle. It will rotate our PCB in a such direction that it can be using this angle whatever we give in such a way that we can visualize it properly. I'm using 100 degree for a Y direction, Y axis. It will rotate my PCB in Y direction by 100 degree so that it can be visualized properly. In the light option there are 4 lights, 4 focus light. It is just like lights used in cricket ground. So I am changing the intensity of it to 1 of all lights. Okay, this is not necessary, but no, you are not bound to use this one. You can keep as it is, but use this 100 generally, or you can choose any one file, any one angle. Now just create POV and exit. Hit over here. Just hit OK. If you use any diode, it will ask for the color of diode. If you use any microcontroller or any processor IC, it will ask for the logo on it. In that way, it will ask little bit question to you. Then just give the little bit information and then hit OK. Go to next, and it will ultimately create a file. Now just open the directory again. Documents, eagle, rectifier. Now you can see a POV array file. POV file is generated. Double click it on it. It will open that software, POV software. Now we already did the initialization whatever we need using in this tool and edit master POV file. Now it is not needed to do again and again. We just open it and just initialize it. Fine. This is the pop-up window. Just choose the highest resolution from over here, 1600 cross 1200, and just hit render. It will give this error. Just ignore it all time. Just hit OK. It is of no mean for you and no use for us. Now look at over here. This will render a 3D circuit or 3D view of our circuit whatever we designed. You can see it. These are the two pads where we are going to connect our transformer through wires. These are 2 diodes. 2 more will become. This is my 7805 regulator IC, which is used for regulation purpose. This is my 2 capacitors. Fine. It will complete. Let it complete. And these are my 2 solder pads for output. You can see it. Whatever this image is generating, it is also stored in the same directory where we are saving all the other files, that is rectifier file. Okay, it will give this indication. Just hit OK and close it. Now close this file. Now go to that library and that directory again. Documents, eagle, rectifier. Now you can see this image is created in bitmap form. You can see it. Fine. For the let's do little bit modification, or you can say makeup over top layer. Fine. For that, what I am doing, I am giving a one copper sheet In the same way where we use the bottom sheet, the same way I am using the another copper layer to the top, just to visualize, or you can say make up for our that 3D view. Now just choose this polygon and then choose a top layer. Width is chosen properly, isolate factor is chosen, that wiring style is chosen properly. Now just go for it. It is just for to see good picture in 3D view. Now save it and again follow the steps. Run. It already opened that 3D folder. 3D41 ULP. Hit OK. Board 200. Light intensity 1. You are not bound to use these values. Select it according to your preference. I am just giving another name to this file, rectifier1.pov, so that it can we can keep that file as well and this file as well. Now create POV and exit. Okay, it will create and give the indications. Now again go to library. You can see this another POV file is generated. Open it. Now initialize it. Choose a maximum resolution and render it. Ignore this error message again and again whenever it comes. Now wait for the image. We did all these things, that is copper layer at the top, we put it for the proper visualization of our 3D view. Now you can see it. A copper layer is put on a top layer, which makes our 3D view very good looking. Is it? Wait until it gets complete. Fine. You can just close this image, or you can rendering of this image for a time being, but it will not get closed. Okay, in background it is running. You can see over here rendering. Fine. Until unless you stop this, it will not complete. Let it be completed in background. It will save it properly. Fine. This is all about our system. This is my circuit diagram, schematic. This is my board layout, and 3D file is rendering. Fine. This is all about your circuit. Now as well, you can put your name, logo over these sheets. Fine. Choose this T. I am putting my name. Okay. Hit OK. I am choosing font as a vector because I loved it. Also it is good looking. Now choose a proper format and you can see this image is completed. Let's see it first. See, proper border is given and this is what a copper layer. Fine. I am giving my name. This red color means that this is on top layer. You can choose it at the bottom layer, because whenever you are going to we generally print the bottom layer, so your name will come at bottom layer. Fine. Just press once your left key of your mouse. You can adjust over here. You can rotate it however you want. I'm putting it at the bottom, or it is good looking over here. Just hit enter just once. It will look like it is not printed, but actually it is printed. Just hit this ratness button once. Now you can see this at the bottom layer it comes. Now just escape once. Again I can put these names on the top layer as well. I'm typing rectifier. Hit OK. Fine. Now I want this to be as a name. You can see this 1N407D3. In images also you can see this. the names and all get printed on this PCB itself. You can see over here. If I want to print it same as it is, same in form, fine, in your hand. Got it? Now double escape for to come out from that window. Again, you can put logos on your circuit. Let's see how the logos will look like. Just search for the logo, expand it. Now you can say CE. C is nothing but whenever any product is compatible with European standard and ready to sell in the European market, this product and the product get this logo, or you can say this is one standard. You can this biohazard also. I'm using the CE 4mm. You can put it over here. Again escape. Now I want to put this eagle sign also. I can put it over here as well. This FCC sign or this don't touch sign you can also put over here. Fine. In this way you can make up your circuit again and again. Now save it. Again you generate your POV file for 3D view. In this way you can put your names and all others. Fine. This is final view of my project. Fine. Okay, again let's summarize it. Initially I'm closing it for a while. What I did, I go file, new, then project. It will create a one file in Eagle library, Eagle directory. Then in this rectifier I created a new schematic. I design schematic first. You can see this. I design schematic first. Then I go for board, design all things properly, and then I render my 3D view like this. Fine. Now double click it on, open it, the board file. Now you can see this, the copper filling is gone. Just use this ratness button to refill it. Fine. All thing is chosen, but you have to just click this ratness button many times. Fine. This is all about my eagle. Let me show you my few examples what I did in eagle. This is the A-stable mode 555 design I did. This is electronic harmonium. Okay, I use a 555 IC, one speaker and a several register. Fine. This is my board file. You can see. Use this ratness button. I put my name and name of my project, harmonium, or you can say it is electronic piano. Fine. Just close it. In my mini project for the as a college demand for the mini project in third year, I did it. Just open it. I designed a digital thermometer using Atmega 32. This is a supply, this is a temperature sensor IC, this is a LCD, this is microcontroller IC. Fine. This is one crystal. I give proper name digital thermometer, and this is my board layout. And just hit this ratness, Atmega IC, LCD crystal. Fine. You can see my 3D views of that also in documents, eagle, mini project. This is my circuit diagram, and this is my 3D view. Atmega IC, LM35T. This is crystal and capacitor reset pin for the power supply. In electronic harmonium also you can see it. Fine. This is speaker. This is a register. Whenever in you get this or you can see it, we left one component here. Speaker should be here, but actually in POV software the library for this speaker is not available, so that why this is this space is left empty, but actually you can put some other documents also not included in that POV software, so don't worry. In this way you can proceed. Now this is a 555 stable in which one LED is used and 555 IC is used. You can put any logo over here just to visualize your, you can say, just a final touch up to your 3D view. Fine. I just forgot to explain you one thing. If I want to use this circuit diagram in my project, or you can say in my abstract or in final result, so I need this circuit, then what will I do? Just go to file, export, and then image. Fine. This will bring this image, bring this circuit in image. Save this file with some name in the same directory in the rectifier. I'm saving it as rectifier itself, rectifier in PNG form. Use the monochromatic, that means the circuit diagram will be in black and white. Use the resolution highest maximum possible. I'm using 999. You can go beyond that also, but I generally use 999. Generally keep the area full and hit OK. It will export that image. Now go to that directory and find it. Search it for PNG file. This is my PNG file. Now you can see your circuit diagram. This is my circuit diagram, label, name, date and time, all things are covered. Okay. This is my final thing. One more thing, if you want to know about your PCB's dimension, then we have a very good shortcut, PCB code. Hit it. You will have a detail about your PCB layout. Number of layer 2, because actually components are in another layer. That's why I accepted that we just use and route our all system in bottom layer, but components are on upper layer. That's why number of layer is 2. This is board name. This is our board dimension. X-axis is 49.2 mm. That is approximately 5 centimeter. And the board height is, that is length is 64.76 mm. That is approximately 6.5 centimeter. Board thickness is also given. It is of no use. We are interested in these two values only. Board dimensions X and Y. Fine. Just close it now. Again, we have a very good option in Eagle 6.5.0 version. This is D-Link. Just hit the D-Link. You should connect it with your internet and then schematic. It will automatically pick out your elements. You can say just see over here 100 microfarad, and it will search on the net for your component. Fine. This D-Link is actually used to send your part list to the manufacturer. Now Eagle is directly connected with element 14. It is the online distributor store, so you can also go through D-Link. But for the engineers studying students, it is not much useful. Fine. To get a part list as well, we can go for export, file, export and part list. Just click and hit BOM.txt. BOM is nothing but build of material. Fine. Whatever components are there, I used to save it using BOM. Worldwide also this is a standard name, BOM, build of material file. I am saving it in text file first. Save it. Fine. Now you can open it, that file, to see actually what it means. BOM. Open it using notepad. Fine. You can see part, values, devices, packages. Okay, you can select these ones. Fine. I think I covered all the topics in the Eagle. All thing. Let me tell you one more thing. If you wanna change the width, or you can say drilling size, after you saved it, after you're saving, you want to change it, because I route all things and did all. Now if I want to change the width of this file, you just have to go over settings. You have a lot of options using drill, size, isolate factor you can choose, but now I need a width. I'm choosing it to 0.8. It is a quite, you can say this. Now after selecting this width setting and this value, now this cursor is just like a magic stick. You just have to stick over the wire get, width of that wire get changed, and you can see it. Fine. In this way you can change the wiring, width of your wire as well. Now I told you already, just hit rat nest after doing any step. See, the spacing is increased, and now your file is ready. Save it. In this way you can do little bit modifications of yourself. This is all about Eagle. Here are some tips for you while using Eagle. I'm just creating new schematic to show some tips. Assuming you need a 555 IC, so after creating this grid and all others, we will add our component. But where will you find this 555 IC? That's the most important. In which library it is hidden? Let me search for timer first, as it is a timer IC. It is not over here. There is no timer library over here. Then where is the 555 IC? How can I find it? Now here we have a search option. Fine. You can just type 555 over here. Now hit enter. Okay, still it is saying that no match. Why it is? Because 555 IC has a it's just not a 555. It is a LM555, any 555. That means company gave their initial name to them, just like a Fairchild had given LM555. National Semiconductor has given any 555. So let's search for LM555. Fine. Still we got no such match. That means this is not included in any library. Now we are searching for an E555. Let's search. We got it. See over here, it is in a ST microelectronics. This is stored in ST microelectronics. Now you can use this 555 IC. Fine. Just press OK. Press OK. You can see that the terminals are not proper. That means 1, 2, 3, 4, 5, not like that. Don't worry. Generally, we used to also draw in this manner. 6, 7, 2 terminal one side, 8, 4 in one side, 3, 5, 1. Because we know that 8 and 4 are the power for the power. 1 and 5 are generally for the grounding. 2 is for trigger, 7 is for discharge, and 6 is for threshold value. That's why it is also set it in that manner, so that we can use it properly, or we can connect the all connections very simply. Fine. But don't worry, this will come in this board file in the proper manner itself. You can see this here. This is terminal 1 2 3 4. All connection will be done properly by this software itself. Okay, fine. Generally many things will not, you will not get in this library. Just use this cross button to go to library again. There are many things you will not get in this library, like potentiometer of your choice, LM35T temperature sensor IC, then MQ6, that is a gas sensor. You will not get in this. For that you need to add a library, external library for it. I told you already how to, just Google it, download the library file and just add it. For the time being, I had downloaded Adafruit. It is also a very good library which includes the some much more important component in a single library, like 555, LM series, LM317 series, 741 series, 741 operational amplifier series in the single library. So I'm just copying it first. Now go to program files, Eagle 6.5.0 library, paste over here. Fine, this is pasted. Now close it. Now we will tell the Eagle to use that library. Use it. Control all and hit OK. Open. Now check that Adafruit library. What's there inside the Adafruit? Let's have a look. Here, open it. 555 timer. You can just expand this also. LM555. This is a surface mounting device. This is the DIB package. NE 555 surface mount, DIB package, SC 555. There are lots of options. This is a diode 11404, 4-pin connector. You can say this is a pin heads, 1x5. This is a headphone jack. We have a lot of options over here. This is Arduino itself. Do my Lenovo. Oh no, you can add it. You have a lot of options. You can say this is a you have a LED also here. 3mm, 4mm, 3mm, 5mm. Pin heads 1x1, 1x2, 1x3. Fine. In this way you have a lot of option inbuilt in this Adafruit library itself. So I will recommend you to download this Adafruit, as well as one more file. We got search it on Google, Spark Fun Eagle libraries. You will get a lots of option in that. In the Spark Fun library, all things are sorted out separately, just like gas sensor, temperature sensor, regulator. You will get in the single library, but inside that library also they are divided properly, so that you can have you can use the many components in a single library itself. Because in general purpose, for a general engineering project, we don't need this much of a library, all libraries. That is important. Okay, now one more thing. uh, Whenever you're going to add, you can say attach one battery, 9-volt transistorized battery to your project, so it is very difficult to put a soldering over there. You need a pin head for that. Generally we use a pin head. Let me show you how it is, how it look like. You can see it in my mini project. I used it. See over here, this is called as a pinhead. In this pinhead, one battery, another female pinhead, you can purchase it from any shop, that will be connected to here. So generally we use this pinheads for the connection of battery. Let's check out where it is. File, new. I'm choosing schematic for show you. It is already created. Now go to add. Now just search for pinhead. And we got it. Now go for 1 cross 2. Right? 1 cross 2, this one pin. Or you can use this one also. This is the vertical one and this is the slipping one. You can choose any one. Fine. I'm using this slipping one. Just okay. Rotate it. Put it back. Fine. In this way you can use this. Go to board file as well. You can see over here. And you can use this. Sometimes you may get conditions like this where you can't connect this wire to this point because already one wire is here, so you can't have a cross connection over here. So what we can do, we can go for another layer of PCB. If double layer PCB is available with you, then quite okay. If not, then you can connect a overhead wire to these points. Okay, for that you will need a one drill over here, so that just choose this route button. Now click over here. I'm changing weight to 0.6 first. Now go to the top layer first. This red is showing that, red color is showing that you are in at top layer. Now you can connect this to this point. Okay. This drill is of rectangular size, so we can change it using this setting tool by shape to round, then click OK. This shows that up till this point the wire is at bottom, and then from this point to this point we are connected using overhead wire, or you can say jumper, or you can go to double side PCB. If you are having a 2-layer copper sheet, then you can go for it.
Electronic circuit boards are the brain of every inverter. Equipped with thousands of components, some of them extremely small, they perform all of the energy conversion, control, and monitoring functions. Utilizing the strength of our more than 500 engineers, we manage all phases of circuit board manufacturing from concept to production in our factory located in Kassel, Germany. In this film, we want to show you the production process. It takes place in 3 main steps. First, SMD assembly. Sensitive components, some very small, such as resistors or diodes, are placed automatically onto the surface of the board. This is called the SMD assembly, for surface-mounted device. Second, THT assembly. Larger components, such as capacitors or coils, are assembled by hand, using through-hole technology. The components are positioned with their leads through corresponding holes. Then they are soldered onto the circuit board. Third, test and coating. After the assembly is completed, the circuit board is electrically tested with a special testing adapter. Once it has passed various tests, the board is finally coated with a protective layer. Currently, there are 4 assembly lines in operation, with a total placement capacity of 230,000 components per hour. At this pace, we produce a new circuit board about every 30 seconds. Between the production stages, each board is checked with automatic optical inspection procedures. In total, 10 optical inspection machines ensure that our high-quality standards are met during the whole production process. Now let's take a closer look at the 3 steps of production. Starting with the SMD assembly. First, solder paste is applied on the board with a solder paste printer. A template ensures that the application of the paste is limited to the points where the SMD components will be placed. Afterwards, the board enters the assembly machine, where SMD components are placed automatically. They are loaded into the machines in reels, similar to film reels. Typical SMD components are resistors, diodes, transistors, or integrated circuits. The smallest of these components are about the size of a pencil point. Therefore, the machines operate precisely but also extremely fast. Each one of the 2 insertion heads can place up to 60 components per second. To accomplish this, they save time by carrying a supply of up to 20 components in a rotary magazine. This allows them to place several components without having to retrieve another one each time. After every component is placed, the board passes through a 23-foot-long furnace. A temperature of 500 degrees Fahrenheit causes the solder in the spreadable soldering paste to liquefy. Now, the SMD components are bonded firmly to the board. Since inspecting small SMD components with the naked eye is not possible, SMA uses an industrial image processing system known as automatic optical inspection to check the predefined parameters quickly and precisely. During each test, 80 images are captured using a special camera. The system then compares these images with reference data in memory, so as to determine possible deviations. In doing so, about 1,600 attributes are checked. The next big step is the THT assembly. The placing of the larger components is accomplished by hand, but also with the greatest precision. At each workstation, a screen shows the exact position and number of the parts to be mounted. Once completed, the board is placed in a matching transport frame. An RFID module on the frame allows the subsequent systems to recognize each type of circuit board automatically. An example of this is the second optical inspection, which SMA is the only inverter manufacturer to apply before the second soldering procedure. Here, about 160 attributes are checked in addition. And if one of the larger components is not correctly in place, this can still be easily rectified. Now the THT components are soldered onto the circuit board. In the wave soldering system, the board is moved slowly over a wave of liquid solder at 500 degrees Fahrenheit. Here, the wire connections inserted through the board are bonded firmly to the circuit board. Last step, test and coating. Once cool, each board is electrically checked. Are all of the components in their place? Are they the correct values? Does the board perform electronically? For each type of circuit board, there is a matching testing device, a rack with up to 800 fine contact pins. When closed, the pins touch corresponding contact points on the board, so that currents or testing signals can be applied and measured. Once the test is completed, the individual firmware is uploaded to the circuit board's memory. Lastly, each board is coated with a protective layer on both sides. The liquid coat of lacquer looks thick going on. but when dry, it will be about the thickness of a human hair. The coating protects the board from dust and moisture and prepares it for a service life of more than 20 years. After drying, the different types of circuit boards are packed into carts and await their further processing, be it in the assembly lines nearby or in Denver, Colorado. Based on these carefully manufactured products, SMA inverters remain the top choice for solar professionals around the world.
Thank you for watching these videos. Hope you had a learning experience from this, and happy PCB designing.